All right, we're going to get started again with our next session, where our talk is going to be on locally verifiable aggregate signatures and cryptographic accumulators. Different names, same thing. And the talk is going to be given by Anaïs. Thank you.
Thank you, Alison. So good morning, everyone. I'm Anaïs, and today I'm going to show you how I failed with Olivier Blasi and Sébastien Canard to prove that locally verifiable aggregate signatures and cryptographic accumulators are actually the same thing. So first, let me briefly introduce you the primitives and the reason I wanted to study their relationship. On one hand, cryptographic accumulators is a well-known and used primitive in cryptography since its introduction in 1994. Informally, an accumulator scheme is a compact representation of a set of elements that allows membership proof for one element. Regarding security, it is required that this membership proof cannot be forged, and as for constructions, well, we can find RSA-based or pairing-based constructions. On the other hand, locally verifiable aggregate signatures were introduced last year at Crypto. Informally, a locally verifiable aggregate signature scheme is a signature scheme that allows the aggregation of a given number of signatures and that also provides an efficient membership verification algorithm to verify if one message given as input has indeed a signature aggregated in the aggregate signature. This efficient membership verification is the main difference with the previously known primitive of aggregate signatures, as we will see later in this presentation. Regarding security, well, it is required that this membership verification for one message cannot be forged, and as for construction, we can find RSA-based or pairing-based constructions. Thus, as you can see, when looking at both primitives, we notice a lot of similarities in the definitions, properties, and even constructions. That is the reason why we wanted to study the relationship, and more especially, at the beginning, I wanted to prove that locally verifiable aggregate signatures are just one kind of cryptographic accumulator. So before to go into the proof, let me define the primitives more in details. Here is a figure that represents a locally verifiable aggregate signature scheme that I will call LVAS for short in the rest of this presentation. This primitive is composed of several algorithms. The first one is the setup algorithm that outputs a pair of signing key SK and verification key VK, where the signing key is secret and the verification key is public. Then there is a signature algorithm sign that takes as input a signing key SK and a message M, and it returns a sigma, a signature of that message. The third algorithm is the verify algorithm that takes as input verification key VK, a signature sigma and a message M, and it returns 1 if sigma is a correct signature of M. If it's not the case, well, it outputs a 0. Then you can find the aggregate algorithm that takes as input a verification key VK along with a set of messages M1 to ML and their associated signatures sigma 1 to sigma L, where all the signatures were honestly computed by the sign algorithm. Notice that in this presentation we will be in the single signer setting, meaning that all the signatures that are aggregated here are computed using the same keys. In the multi-signer setting, you can have different keys for different signatures, but we will not consider this in this presentation. This aggregate algorithm outputs an aggregate signature hat sigma. And then there is an AgVerify algorithm that takes as input the verification key VK, an aggregate signature hat sigma, and a set of messages M1 to ML. It returns 1 if each message here has a signature that is aggregated in hat sigma. If it's not the case, well, it would put 0. Then there is the local open algorithm that takes as input a verification key VK, an aggregate signature hat sigma, a set of messages M1 to ML, and an index int that belongs to the set 1 to L. This algorithm returns some auxiliary information that we will call augs, that is about the message int, and it's a signature. And finally, the last algorithm is the local AgVerify algorithm that takes as input the verification key, an aggregate signature hat sigma, one message mInd, and it's an auxiliary information augs, and it returns 1 if a signature of mInd is indeed aggregated in hat sigma. But as you can see, this verification algorithm is more efficient than this one in the sense that it does not take as input all the messages. So here is the formal definition of an LVAS scheme. As you may have already noticed, we can find the three algorithms setup, sign, and verify that compose a signature scheme, along with the two algorithms aggregate and agverify that compose an aggregate signature scheme. And finally, there are two other algorithms that were introduced last year, the local open and local agverify algorithms. So what about security? Well, in this presentation, I will give you all the security properties through a security game between a challenger and an adversary. So here is the aggregated unforgeability with adversarial opening security game. In this security game, the adversary is given the verification key of the scheme, and she must be able to output a tuple composed of a message M star, a forged aggregate signature hat sigma star, and a forged auxiliary information aux star. Then we say that the challenger wins if the local agverify algorithm on input the tuple given by the adversary returns 1. If it returns 0, then we say that the adversary fails. Notice that in this security game, the adversary is allowed to query the challenger to obtain some signatures at the condition that M star is not queried. So now let me present you more in detail the second primitive, cryptographic accumulators. To be more precise, there are two kinds of cryptographic accumulators. This was formally named and established in 2014 by Kumar et al. You can find asymmetric accumulators and symmetric ones. In this presentation, I will mostly be talking about asymmetric accumulators. Thus, when I will be referring to accumulators, I will be talking about asymmetric ones. But here, I will give you both definitions. So an accumulator scheme is composed of a generation algorithm that outputs a pair of secret and public key, where the secret key can be empty. Then there is an evaluation algorithm that takes as input the keys of the scheme, along with a set of elements X, and it returns a compact representation of this set of elements, called the accumulator of X. In the case of asymmetric accumulators, there is an additional algorithm, with create, that takes as input the keys of the scheme, along with an accumulator and its associated set X, and an element Y, where Y belongs to the set X, and it returns some auxiliary information that we called a witness. And the last algorithm is the verify algorithm that takes as input the public key of the scheme, an accumulator and an element Y, and in the case of asymmetric accumulators, its witness, and it returns 1 if Y is indeed in the set represented by the accumulator given as input. If it's not the case, well, it would put 0. So here is the formal definition of accumulators. So as you already noticed, a symmetric accumulator is an accumulator in which the verify algorithm does not need to take as input auxiliary information. Only the accumulator and the element Y are required. And also notice that for the eval and with create algorithms, well, they can take as input either only the public key of the scheme or only the secret key, or both keys. It does not matter, but this will be important in the rest of this presentation. So now let me briefly present you a security property required for asymmetric accumulators. This is only one security property through the many that exist for accumulators, but we will only need this one. So it is called collision resistance. In this security game, the adversary is given the public key of the scheme, and she must be able to output a set of elements X star, along with an element Y star and a forged witness for Y star. And we say that the adversary wins the game if Y star does not belong to X star, and the verify algorithm on input the accumulator of X star, compute honestly by the challenger, and Y star and its forged witness returns 1. If the verify algorithm returns 0, then we say that the adversary fails. Again, notice that the adversary is allowed to query the challenger to obtain some witnesses or accumulators, and this time without any restrictions. Okay, so now let us see that both primitives are the same. Our idea was simply to try to build one from the other, then to do the construction the other way around. We first start with the creation of an accumulator scheme from an LVAS scheme. Our idea for the generation algorithm is to define it such that it runs the setup algorithm of the LVAS scheme, and therefore we obtain that the secret and public key of the accumulators are respectively the signing and verification key of the LVAS scheme. For the evaluation algorithm, we can define it such that it runs the sign algorithm on all the messages here M1 to ML that represent the set X here to be accumulated. And then it runs the aggregate algorithm on all the obtained signatures. Doing so, we obtain that the accumulator is actually an aggregate signature. For the with create algorithm, well, our idea is simply to use the local open algorithm. As you can notice, both algorithms are consistent in the inputs with our previous definition of the signature and of the evaluation, sorry. And therefore, we obtain that the witness is the auxiliary information of the LVIS scheme. And for the verification, well, again, we simply run the local verify algorithm of the LVIS scheme, as again, both algorithms are consistent. So this construction is working quite well. Well, that's good. We did not fail at this one. Let's see if we can do the other one. And later on this presentation, I will come back on the security of this first construction. So for the second construction, we need an accumulator with a property called addition or additive accumulator. In this accumulator, there is another algorithm called add that takes as input the keys of the scheme, along with an accumulator and its associated set X and an element alpha, and it returns the accumulator of the set X union alpha. Notice that this accumulator here can then be used for witness creation or directly for verification. Also notice that the accumulator output by the add algorithm is the same as the one you will obtain if you run the eval algorithm on the set X union alpha directly. The only difference is that if you already know the accumulator of X, it is more efficient to run add than to run the evaluation algorithm again. So here is the formal definition of an additive accumulator, and it is important to notice that the add algorithm takes as inputs either both the keys of the scheme or only just one, and no matter which one. So for our construction, we need a special kind of additive accumulator. We said that this accumulator has private evaluation. It means that the eval algorithm takes as input only the secret key of the scheme, and we want it to have public addition and public witness generation. Thus, we need an add and with create algorithm that takes as input only the public key of the scheme. So from that, let us see that we can build an LVIS scheme. So for the setup, well, we can do as we did in the previous construction. You just have to swap both algorithms. We obtain the same thing for the keys. Then for the sign algorithm, our idea is simply to define it so that it runs the eval algorithm on a set composed of one element, here X, which represents the message M2 signed. Therefore, we have that the signature is an accumulator. For the aggregate signature, for the aggregate algorithm, the idea here is to notice that in these two figures, message M1 here corresponds to the set X1 here, to the set composed of the element X1 here. And with our definition of the sign algorithm, we have that sigma 1 here is actually the accumulator of the set that contains the element X1. And thus, our idea for the aggregate algorithm, well, it's simply to run the add algorithm several times. We start with the accumulator of the set that contains only the element X1. We add X2 to it, and we continue until we have added all the L elements, which are all the messages M1 to ML that we wanted. Doing so, we obtain that the aggregate signature is actually an accumulator. For the definition of the local open algorithm, well, we do as we did in the previous construction. It simply runs the with create algorithm. And thus, the auxiliary information is the witness output by the with create algorithm of the accumulator. For the verification algorithm, well, the idea is to run the witness creation algorithm here for the elements Y that represent message M here, and then we run the accumulator verify algorithm, and the LVIS verify algorithm outputs the accumulator verify algorithm outputs. For ag verify algorithm, well, we do the same, but we compute witnesses for all the elements, thus all the messages. And then if at least once the verify algorithm of the accumulator outputs 0, then so does the ag verify algorithm. And for the last one, well, we can do as we did in the previous construction. So at this point, we were quite happy because we think, yeah, we succeeded, we made what we wanted to do. But actually, there are some limitations, and especially regarding security of these two constructions. So for the first construction, there is no limitation except for security, but I will be talking about this in a few minutes. But for the second construction, you notice that we require the special kind of accumulators. And this might be complicated. Indeed, until really recently, there was no accumulator with private evaluation and public witness generation. So now we know that such a scheme can exist, but the problem is this existing accumulator does not have a public addition. Therefore, this construction might not be possible if you cannot find a specific accumulator to start. And so what about security? Well, we tried to make a security reduction from one adversary to the other, and we noticed several issues. First, when you look at the outputs of both adversaries, while we can easily identify the element Y star and its forged witness to the message M star and its forged auxiliary information, the question is more tricky when looking at the other outputs of both adversaries. For example, imagine that you want to build an LVAS adversary from an accumulator adversary, then how will this set X star here help you in forging an aggregate signature? And the question is working if you want, also in the other way around. If you want to build an accumulator adversary from an LVAS adversary, how will this aggregate signature help you in finding a correct set? And unfortunately, we failed to answer to these questions. But we also noticed another issue. In this security game, the accumulator adversary is allowed to query the challenger to obtain accumulators. She does not have to query the challenger to obtain witnesses anymore, as witness creation is publicly done. And these queries can be done without any restriction. On the other hand, the LVAS adversary has some restriction on the queries she can make. So imagine the following situation. You want to build an LVAS adversary from an accumulator adversary. At some point, the accumulator adversary might ask for the evaluation of a set X, such that Y star is in X. And by our definition of the accumulator, the LVAS adversary cannot answer to that query, simply as she cannot query the challenger for the signature of element Y star. And this might impact the accumulator adversary advantage to win. It's a security game, and unfortunately, we were not able to estimate how this will impact this advantage, and if this advantage will still be non-negligible. So before to conclude on this presentation, as you may have noticed, an LVAS scheme is composed of the algorithms that compose a signature and aggregate signature schemes. Thus, it is quite natural to ask ourselves, is there a relationship between signature and aggregate signature schemes and accumulators? So we tried to do this again, and we failed. So let me briefly give a word about these other failures. Here I will be talking about symmetric accumulators are in signature and aggregate signature schemes. The verification algorithm does not need to take as input auxiliary information. Therefore, it is more relevant to use a symmetric accumulator rather than an asymmetric one. So for the construction of a signature scheme from a symmetric accumulator, well, again, this is possible at the condition to find the perfect accumulator, and this might be complicated in the case of symmetric accumulators, simply because they are mostly based on symmetric cryptographic primitives, and as verification might be public, then it seems to be complicated to have a private evaluation. For the construction the other way around, well, we obtained something that was working, except that we have a bond on the accumulator, which is equals to 1. It means that you can only represent a set composed of one element. Thus, it's not really relevant. Then we did the construction of an aggregate signature from a symmetric accumulator, and again, it was working under some conditions. And the last construction was the construction of a symmetric accumulator from an aggregate signature scheme, and this one was not working, simply because the verify algorithm of the accumulator is expecting only one element, while the verify algorithm is expecting all the messages. Therefore, we cannot define this verification algorithm such that it runs this one, as we will not have enough inputs. And what about security? Well, we failed again, as for the previous constructions. So here is a table that summarizes all the constructions we tried to make. As you can see, this one in red is not efficient, in the sense that the obtained aggregate signature is not more efficient than the trivial solution that consists in computing all the signatures then sending the concatenation of all of them. Thus, it is not quite relevant to do such construction. And the best construction we have is the construction of an accumulator scheme from an LVIS1. And as for security, well, the problem might come from the fact that we are missing some security properties for accumulators. For those who know a little bit more about accumulators, there are two kinds of security properties for them. Properties that protect witnesses from forgery, and some others that protect the privacy of the set represented by the accumulator. But there is no property that protects the forgery of the accumulator itself, especially when its compute is done secretly. So finding these new security properties for accumulators might solve our issue. And unfortunately, so at this point, we are not able to answer the question, is locally verifiable aggregate signatures and cryptographic accumulators the same thing? Thank you.
All right, we're actually ahead of schedule today, so we have plenty of time for questions if people want to come up to the microphones. In the meantime, I have a question. So one, just thank you for this lovely table of so many failures. We really appreciate that sort of thing here. I'm curious if, given all of this, do you believe that these are the same thing, or do you think that somewhere in this are the seeds of a kind of black box separation or some other kind of fundamental barrier?
Well, I think actually they are not the same thing, especially as you may recall, I was talking about single signer setting for locally verifiable aggregate signatures, and the multi-signer setting is not something that exists for accumulators. So I'm afraid that both are different, but to be honest, I need a little bit more time to look at authorities accumulators primitive, if it can exist and if it will be the same as the multi-signer setting for LVIS scheme.
Are there any questions from the audience? So one other question about the process of sort of going through these different approaches. Did the places where these failed kind of line up with the intuition that you and your co-authors had, or were you surprised by sort of where the failures ultimately ended up being?
Well, for the security failure, it was something that we saw quite straightforward. Because the thing is, we attended the presentation last year of locally verifiable aggregate signatures, and at the end we were, oh, that's something we understand from the beginning to the end, and it's perfect, it's because we know it. But when you look at the security definitions, if I can come back, well, this one will be enough. For the asymmetric case, here you have to produce a set and the accumulator is computed honestly, while here the aggregate signature is forged. And this is something that comes straightforward into our minds. There is another security property for accumulators where the accumulator itself is forged. You do not have to give such a set. But the thing is, such accumulators are also providing non-membership proof. And the question is, what will be non-signature? It's kind of complicated, so it's not a surprise regarding security. It seems that both are different things.
All right, we have a question in the back. Would you come up to the microphone, please, so that we get it on the recording? Thank you. I feel like I should have some background music while this is happening. Do, 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 do. All right, thanks. Yeah, speak right into the mic, please.
So you said that maybe.
Yeah, okay. Thank you.
You said that maybe with additional properties of the accumulator, it might be possible to construct things. I was specifically thinking about the restrictions, about what I'm allowed to ask about. Is there a reasonable, I guess, construction, not construction, but is that a reasonable thing to even add to an accumulator in a regular setting, kind of having restrictions on what you're allowed to query for the reduction to work, I guess?
Well, while the restriction on the LVIS adversary is quite natural, it is more complicated to answer that question for the accumulator. And in all the security constructions, security properties right now, you do not have such restriction. So we were working a little bit on finding new security properties for accumulators. And for now, we do not succeed to obtain such properties. And I think that even if we were able to solve that issue, this one here will be another one really important. And we may fail again.
Thank you.
Any other questions? All right, let's thank our speaker again. Okay, a couple of quick announcements for later in the day. So this evening, the RISE workshop, which stands for Research Insights and Stories for Enlightenment, which is happening mostly tomorrow, is having a Story Slam event this evening, starting at 5:45 here in Corwin in the outside area there. They'll have drinks and they'll have food and they'll have a bunch of people telling stories about their experiences in cryptography and other things. So that starts at 5:45. This evening. More details can be found on their affiliated event website. As for us, we're going to take a little break here because we want to start our invited talk at 11:40, and that will be a 1-hour talk that will last until our lunch break. So I'll see you back at 11:40.